Last week, we studied geometric optics, which is concerned with the direction of motion of light. This week will be wave optics, which is a different part of the theory of light. What's the difference between geometric optics and wave optics? Remember, in geometric optics, we used ray tracing to analyze the direction of light. So the rays show the direction of propagation. But it doesn't really take into account the fact that light consists of waves in the electric and magnetic fields. Light consists of electromagnetic waves, and the fields obey the superposition principle. So when waves overlap, they interfere. Let's consider two electromagnetic waves and suppose the electric field in some direction is an amplitude A1 times cosine kx minus omega t plus a phase shift delta 1 plus an amplitude A2 times the cosine kx minus omega t plus a different phase delta 2. So this is a wave traveling in the x direction. It oscillates in both x and t. And I'm assuming that I'm adding two waves with the same frequency, the same k value. Now, constructive interference occurs when the phase angles, delta 1 and delta 2, are the same. Let's say they're both 0. Then I'd have cosine kx minus omega t and another cosine kx minus omega t times A1 plus A2. So the maximum field would just be A1 plus A2. That would be the amplitude of the combined wave. So take both A1 and A2 to be positive. That means the combined wave has an electric field which is larger than either E1 or E2. Remember the energy or the intensity goes like the field squared. So if A1 and A2 were equal, the electric field would be larger by a factor of 2, and the energy would be larger by a factor of 4. That's constructive interference. Destructive interference occurs when delta 1 and delta 2 differ by pi radians. So, in other words, here I would have, suppose I take delta 1 to be 0 and delta 2 to be pi, then this would be cosine kx plus omega t. This would be minus cosine kx minus omega t. So when I add the two fields, I would get A1 minus A2 times the oscillating factor. So that means that E max, the amplitude of oscillation, would be A1 minus A2. To make it an amplitude, we could take the magnitude, the absolute value. So this will now be less than either of the combined waves. In fact, if we had A1 and A2 equal, E max would be 0. The electric field would just be 0. So that would be complete destructive interference. You would have two waves overlapping, and the combination would be no wave at all. Much of chapter 22 concerns interference in some way or another. The first section of chapter 22 is called interference. Now, overlapping incoherent light beams do not produce interference effects. So here's a picture of two completely separate flashlights, and their beams are crossing, but they're completely incoherent. So the electric and magnetic field oscillations in one beam are completely separate from those in the other beam. Incoherent light beams just pass through each other with no obvious interference. Overlapping coherent light beams produce interference patterns. They'll produce regions of bright and dark called fringes, which occur in the directions of constructive and destructive interference. So where you have constructive interference, you have bright light because the two waves add together. We have destructive interference, you have possibly no light at all, where the two waves cancel each other out. So here's an example where you might have coherent light. Coherent light is not easy, two coherent beams. That's going to require some special technique to make the the oscillations in one beam coherent with the oscillations in the other beam. So here's a schematic diagram of a device called a Michelson interferometer, invented by the American physicist Michelson. It has a light source, a beam splitter. Part of the beam reflects from this beam splitter and hits a mirror and comes back. Part of the beam goes through the beam splitter, hits this other mirror and comes back. Part of these returning beams continue through to the observer. Well, the oscillations in this final beam will be completely coherent, where you have a crest in the wave that went and reflected from M2, and where you have a crest that reflected from the beam from the mirror M1. They'll both be aligned in space and time, and so you'll have constructive interference. So for some directions, you'll have that constructive interference. For nearby directions, you could have destructive interference. And so actually, if you have a narrow beam and a microscope, you would see where the beams recombine an interference pattern, a region of alternating bright light and dark regions, dim light, an interference pattern. So one thing to remember is that interference requires a special kind of superposition. It requires a superposition where the two superimposed waves are coherent with each other. They're sort of in phase or out of phase. All right, now we're going to look at some examples of light interference for the rest of chapter or section 1. The first example is called thin film interference. Here's a photograph. See if I can blow this up a little bit. You have oil on the ground and sunlight striking the oil. Let's say the oil is on a mud puddle. So you have a puddle of water, and on the surface of the water there's a slick of oil. Then you have sunlight reflecting from that slick of oil. You'll see alternating rings with different colors. Now remember, sunlight contains all of the wavelengths equally, all of the colors equally. Sunlight is white, which is a superposition of all the colors equally. So what you're seeing here is that for some radii, one particular color is in constructive interference. And so the reflection from that radius is going to be predominantly that color. And if you go to a different radius, it'll be a different wavelength, which is constructively interfering. And so that'll be a different color. And you get this alternating color, kind of the same order as in the rainbow. Red, orange, yellow, green, blue, dark blue, violet. What causes this is light from the sun reflects from the oil. It can reflect off the top surface, or it can be transmitted through the oil and reflect from the bottom surface. So here there's a reflection between air and oil. Here there's a reflection between oil and water, a reflection at the interface between air and oil, or at the interface between oil and water. Now, the outgoing waves, the wave that was reflected from the top surface and the wave that was reflected from the bottom surface, will overlap. And they will be coherent because really it's the same wave just following two different paths. And so, the crest of one wave will come off, and the crest of the next wavelength, let's say, will go the additional distance and come off and be in phase with the reflection from the top surface. So you'll have a phase locking between the two reflected waves. That's coherent light. And where the waves are in phase, you'll have constructive interference. When they're out of phase, you'll have destructive interference. So here's a kind of diagram which shows one wave has a shorter path length than the other wave. The second wave traveled farther by an amount 2 times the thickness of the oil. So the thickness of the oil will determine, and the wavelength will determine if the two outgoing waves are in phase or out of phase, constructively interfering or destructively interfering. All right, so if the path difference is equal to an integer number of wavelengths, then the two outgoing waves will be in phase. You'll get constructive interference for a particular value of wavelength. If the thickness, it's actually traveling through the oil twice, so 2 times the thickness is equal to 1 wavelength, or 2 wavelengths, or 3 wavelengths, an integer number of wavelengths. So that allows you to calculate what thickness produces constructive interference for any particular wavelength. And that's in the book, and I won't go over it in the screencast here. I'll leave that as an exercise for you. Just look it up in the book. For monochromatic light, that is to say one particular wavelength, what thickness produces constructive interference. Is that thickness unique? No, because the path difference would have to be an integer number of wavelengths. So it could be one wavelength, it could be two wavelengths, it could be three wavelengths. So there can be multiple possibilities for constructive interference. And of course, if you're halfway between two constructive interference cases, you'll be at a destructive interference case. So what thickness produces destructive interference? So take a look at the book and write down the answers to this exercise. That'll be helpful to you when you come to do the lawn kappa problem if you've got that written down. So that's thin film interference. A little more laboratory sort of case is a little device which produces Newton's rings. So let's blow this up a little bit. Newton's rings is a little demonstration of interference of light. It was developed by Isaac Newton. Oddly enough, he didn't understand what he was seeing. Newton didn't believe in the wave theory of light. He believed that light consisted of a stream of particles. But the only really acceptable explanation of Newton's rings is based on the wave theory of light. So he had an explanation, but his explanation really wasn't correct. You have a flat plate, and on that flat plate you have a lens in which one side of the lens is flat and the other side of the lens is curved. And light coming in from above will go, well, part of it will be reflected, but what we're interested in is the light that gets transmitted into the lens and then reflects off the curved surface of the lens. That produces one path, or light can go into the lens and then out of the lens and then reflect from the upper surface of the glass plate below, reflect back, go back through the lens, and form a second optical path. And these two waves have gone different lengths. This one has gone to the base of the lens and back out. This one has gone beyond the base of the lens and then back out. So it has an extra distance. If that extra distance is an integer number of wavelengths, you would have constructive interference. Actually, it's a little more complicated than that, because in some cases for reflection, there's an additional 180-degree phase change upon reflection. Here you have light reflecting from incident light coming from glass into air. Here you have a reflection of light that comes from air onto glass. They'll have a 180-degree difference in their phase. So if the path difference were one wavelength, that would be a dark ring, because the two paths would be 180 degrees out of phase. So the bright fringes will occur where the path difference is like 1 1/2 wavelengths, or 2 1/2 wavelengths, or half a wavelength. And where the path difference is an integer number of wavelengths, because of the additional phase change, there'll be a dark fringe, a region of destructive interference. So you'll get, because everything has this circular symmetry, I mean, here's the axis of the lens. Everything is cylindrically symmetric about that axis. You'll end up with fringes in the form of rings, bright and dark rings. Now you could do this with white light, and that would produce something similar to what we had over here in the case of sunlight hitting an oil slick. But if you do this with one color, say red, then you'll just get alternating bright and dark fringes. So this is a picture from the book. A lens on a flat glass plate. Newton's rings arise from the difference in path lengths for the two exiting rays. The two rays that are coming back into your eye. You know, here's the source of light, the incident ray. Here's your eye, which is observing this pattern. Now, as I say, we could analyze the geometry of this to calculate the phase difference, or the path difference rather, depending on the radius. You know, if the light comes in out here, there's a larger path difference. If it comes out down here, there's a shorter path difference. So these correspond to, as we go out from the center, these correspond to different radii. So I won't derive the formula, but it's in the book. You'll need it for the long kappa exercises. For monochromatic light and normal incidence, so we could consider light coming in at an angle, but the simple cases where light comes in perpendicular to the flat surfaces. So for monochromatic light and normal incidence, what are the radii of the bright fringes, or the bright rings? And conversely, what about the dark rings? At the center, there's a dark spot. That's the region where there's no path difference. You know, that's the region where the concave part, or the curved part of the lens, is right in contact with the flat plate. So the difference in distances would be zero. So the optical path difference at the center is zero, but you have destructive interference, giving a dark destructive interference. That's because there's a 180-degree phase difference between the two reflections. You know, one reflection goes from a high density into a low density, glass into air. The other reflection goes from a low density to a high density, air into glass. And those reflect in different ways, which differ by 180 degrees in the phase of the reflected waves. All right, so those are two of the examples from that first section in chapter 22. And you need the equations for bright regions and dark regions. You'll find formulas for that in the book for both cases. The next section in chapter 22, section 2, is called double slit interference. So let's blow this up a little bit. You have light. It has to be coherent light. So here are the wave fronts of the coherent light coming toward a opaque screen with two slits cut in it. So here's the incoming light. And I don't draw it as a ray anymore. I draw the wave fronts. So let's say these are the crests of the electric field. Now, some of the light will go through this slit. Some of the light will go through this slit. The light that's not incident on the slits will just be stopped by the opaque screen. So you'll sort of have two sources of light to the right of the screen, namely one source of light at this little thin slit and a second source of light at this thin slit. So this is a top view. You're looking at this from the top down. This slit, the opaque screen looks like this in a front view. It's got an opening here, that's one of the slits, and an opening here, that's the other slit. And there's a source of light in back of it, and then there's light coming out here through the two slits. Now the distance between the two slits we could call, we could call it, I don't know, A or something. And of course, we would have some wavelength. So the wavelength of the incident light would be lambda. Now there's also a third length parameter in this problem, which is the width of each slit. We might call that W. But for this section, we're considering cases where W is very small. So W is, compared to the other wavelengths, 0. So we really only have two parameters, the wavelength and the distance between the slits. And the third distance, we just set that equal to 0. Now coming out of this slit, we'll have a set of cylindrical wavefronts. Each one acts like a little filament of light, a thin source of light. Well, the light comes out in all directions, all directions to the right, making cylindrically shaped wavefronts. So from the first slit, we have waves going out this way, we have waves going down this way, we have waves coming out this way. From the second slit, we have waves going out this way. Probably put those in a different color. Well, no, they have to be in the same color because they're the same wavelength. It's really the same, came from the same beam, so we have some waves coming down here. Well, the picture shows those two waves coming from the two sources overlap. And so they interfere. And in some directions, there'll be constructive interference. And so that will lead to high intensity. Those are the bright fringes. But in some directions, they'll interfere destructively. And that will lead to, in fact, a dark fringe approximately 0 intensity in some directions. So if you project the light onto a screen and take a photograph of it, it'll look like this. This picture is not really to scale, but it depends on how far apart the two screens are. But anyway, you'll have a region where there's light incident on the far screen and alternating bright and dark fringes. The central fringe will be bright. So this is blow this up a little more. This is the central bright fringe, this one here. That's because the path length from the two sources is the same for the central fringe. So those two waves will be in phase where they overlap on the screen. And so there'll be a bright fringe, there'll be constructive interference at that point. But if you go away from that point, there will be a path difference between the two sources. And if that path difference is half a wavelength, then those two waves will be out of phase 180 degrees. When they're added together, they'll add up to 0. So that will be a low intensity, a dark fringe. But if the path difference is one wavelength, then they'll again be in phase on the screen, and you'll have high intensity. So you go from the central bright fringe through a dark fringe, back to another bright fringe, through another dark fringe, back to another bright fringe. You'll have alternating bright and dark fringes, either to this direction or to the opposite direction. So this is, as it says here, photo of an actual interference pattern shown after alternating bright and dark fringes. Now you can derive the equation for the directions. The directions, let's say, with respect to the central axis. The central axis would be angle 0. That would be a bright fringe. But at some angle, there'll be a dark fringe. And at some additional angle, there'll be a bright fringe again. So you'll have alternating angles which correspond to bright and dark fringes. Let's see. We should read the figure notes here. Along these lines, crests and troughs and where the crests and troughs meet, you'll have constructive interference. Where lines of constructive interference interact with the screen, or intersect the screen, bright fringes appear. So these are the cylindrical wave fronts I mentioned, plane waves incident, and the interference pattern. So double slit interference results when coherent light from a single source, so these are all in phase, pass through closely spaced slits. The effect is seen when the separation between the slits is something not too far away from the wavelength. So you get noticeable bright and dark fringes when lambda, the wavelength, and A, the separation of the fringes, is kind of comparable. Not equal, but of comparable size. So again, I won't go through the derivation and write down the final formula, but it's in the book. I'll leave it as an exercise for you to look it up in the book and write it down in your notebook, because you'll need to use it when you do the long kappa problems that involve double slit interference. For monochromatic light, what are the directions of the bright fringes or the dark fringes? Why is the central fringe bright? Well, I said that before. Because there's no path difference from the two slits to the central position. So those have the same path length, they'll be in phase. Now, two-slit interference was observed in an experiment which was very influential in the theory of light, which is called Young's experiment. It was done by Thomas Young 1801, so the beginning of the 19th century. Here's a little simpler picture than what I have over here. Here's a kind of a simplified picture, but it's the same thing. You have light from a source. Thomas Young used the sun as the source. It passes through one slit, making plane waves, or almost plane waves, coming from that source. So here's an opaque screen with a slit cut in it so that the sunlight can come through. Well, because it's coming from the same source, those waves will form like a plane wave. The wave fronts will be in phase at the two slits. So then he had a second opaque screen with slits cut through it. This is the top view, this is the side view, and the sunlight would be partially going through slit 1 and partially going through slit 2. In other words, slit 1 acts as a source. Slit 2 acts as an identical source. And, you know, the waves coming out of those two sources will form cylindrical wavefronts. And where the cylindrical wavefronts are in phase, you'll have constructive interference. So this will be the direction of constructive interference. This would also be constructive interference. This would also be constructive interference. And between the regions of constructive interference, there's a region where the waves are 180 degrees out of phase. The crest of one wave would be coincident with the trough of the next wave. If you add the crest and the trough, you get 0. So you'd have no intensity in these directions. So these would be the regions of destructive interference. And if you project it on a screen, you'll see a bright fringe, a dark fringe, a bright fringe, and in fact you could see a whole series of bright and dark fringes in either direction from the center. The reason this experiment was so important was it really proved that light is a wave. There were two theories of the nature of light at the time of Thomas Young. One theory was that light consists of waves, and that was associated with the Danish physicist Huygens. And the other theory, which is associated with Isaac Newton, who was a great expert on optics, was that light consists of a stream of particles. In England, everyone believed that light was a stream of particles because they were all influenced by Newton. But in Europe, on the continent of Europe, people tended to agree with Huygens that light consisted of waves. But they didn't have any proof. They really didn't have any proof of that. They just had Huygens' theory. Well, Young's experiment, which was of course done in England, proved that these are waves. You know, you can probably read about Huygens' principle in the textbook. Huygens' principle says that the waves will spread out and interfere, and where they interfere constructively, you'll have bright region, and where they interfere destructively, they'll have a dark region. You can't really explain those bright and dark fringes by streams of particles, although Newton tried to do it, but Newton just was biased in favor of the atomic theory. He believed that matter consisted of atoms, and he was right about that. Not that he had any proof, but that's just was his theory. He thought, well, light probably is also particles, just like matter. Well, he was wrong about that. Anyway, Young's experiment really had no explanation within the particle theory of light, and it was very naturally explained by the wave theory of light. So Young's experiment for most of the scientists of the day, proved that light is a wave. There were still some holdouts against the wave theory of light, especially in England. Even some well-known optical scientists continued to believe Newton must have been right because he was the great master. But they were wrong. Now this is 1801. Later, 1865, a number of years later, Maxwell, based purely on theoretical analysis, mathematical analysis, showed that light is an electromagnetic wave because he had a wave theory, he had a field theory of electricity and magnetism in which one description or one prediction of the field theory was the existence of waves. And when he calculated the speed based on electric and magnetic force parameters, he found the speed is equal to the measured speed of light. So came to the conclusion that light is electromagnetic, and furthermore, not just visible light, but there's a whole infinite spectrum of electromagnetic waves. So that was 60 years later. So Young's experiment kind of convinced most scientists that light consists of waves, but it was Maxwell who showed those waves are waves of the electric and magnetic fields. Now, later, let's say in the 20th century, the early part of the 20th century, another 35 years later, it was discovered that energies are quantized. Energy is quantized. And in particular, the electric and magnetic fields are quantized. They're quantized fields. And the excitations of those quantized fields had a smallest size. The smallest excitation of the electric and magnetic quantum fields is called a photon. So it took about 30 years to develop the theory to the point where it could be used accurately. But over a period of 30 years in the early 20th century, the theory of the photon was developed. And in that theory, light consists of a stream of photons. In some ways, photons are like particles. In some ways, they're not like particles. I mean, they aren't like particles because they have no mass. But they are like particles because they have energy and momentum described within the theory of relativity by the same formulas as for particles if you set the particle mass equal to 0. So the later theory, the current theory of today, is that light is an excitation of quantized fields, and there are discrete little packets of energy, which we call photons. Those photons undergo interference. So in that sense, they're not like particles. Particles, well, actually, in quantum mechanics, even particles undergo interference. Because in quantum mechanics, a particle is described by a wave function. It's a probability wave. So, for example, electrons are excitations of a quantum field, the electron field. Just like photons are excitations of the electric and magnetic fields. Well, there's also an electron field. So electrons have wave characteristics as well as particle characteristics. And photons have wave characteristics and particle characteristics. So the distinction between light And matter is a little bit less in quantum theory than it is in classical theory. Okay, so chapter 22 is about the wave nature of light, wave optics. And we've seen how, well, the first two sections describe how light waves can interfere, and some examples of that. Now, another property of waves is called diffraction. All waves undergo diffraction, so light should undergo diffraction. Let's try to blow this up a little bit. So that's the third section of chapter 22, is diffraction. And in particular, this is really a wave phenomenon, but in particular, diffraction applied to light. So what is this word, diffraction? Maybe you haven't used this word in everyday life. What is it? Well, you could do a Google search. You could type into Google, what is diffraction? And you'll get a whole lot of answers. Here's an answer that comes directly from Google. So this is just a quotation from Google. Diffraction is the process by which a beam of light or other system of waves is spread out as a result of passing through a narrow aperture or across an edge, typically accompanied by interference between the waveforms produced. So, according to Google's definition, or Google's answer to the question, what is diffraction? Diffraction is a process. It's a process where a wave spreads out as it goes through an opening. So let's suppose we had a slit here in an opaque screen, and this is the top view. So this is the top view of an opaque screen which has a slit cut in it, a little aperture. So the side view would look like this. It's the opaque screen and the slit. So here's the side view. So that's an example of an aperture. Now suppose you have waves hitting this aperture. So let's put the wave fronts in red. So let's put the wave fronts in approaching the aperture. So here are some wave fronts approaching this screen. Now, what are we going to get on the other side of the screen? Well, you might say, well, the screen casts a shadow. So over here you'll have a wave that just is the same width as the width of the slit. So you have wavefronts like this. And outside of the region downstream from the slit, you'll just get darkness. That's the shadow cast by the opaque screen. And that's what would happen in the particle theory of light. That's not what happens in reality. So let's get rid of that, because that's not what we observe. What we observe is the waves spread out as they go through the slit. And so we'll have some intensity going straight down from the slit, but we'll also have some intensity traveling away from the direction downstream from the slit. If this slit is very narrow, then we would have cylindrical wave fronts by the symmetry. There's a kind of cylindrical symmetry. But if this slit is not very narrow, then these wave fronts will not be perfectly circular, perfectly cylindrical, but still the waves will spread out as you go downstream from the screen. That's diffraction. As light goes through an opening or past an edge, it spreads out. And that's what it says. As a result of passing through an aperture, the waves spread out. Here's another, that same Google search will produce probably thousands of hits. Here's another hit from Wikipedia. Diffraction refers to various phenomena that occur when a wave encounters an obstacle or opening. It is defined as the bending of waves around the corners of an obstacle or through an aperture into the region of geometrical shadow of the obstacle or aperture. So I've drawn here the shadow is the shadow of the screen. I could also consider waves incident on a little object. And then the shadow would be down here. And you might think that the waves would just go out this way and you'd have a shadow in this direction. There'd be no intensity downstream from the obstacle. But that's not what happens. What happens is you have waves coming out in all directions. Because as they go past the edge here, they spread out. So they spread out into the region which geometrically would be the shadow. So this refers to a geometrical shadow, but it's not the light shadow. There is no light shadow. The diffracting object or aperture effectively becomes a second source of the propagating wave. The Italian scientist Francesco Maria Grimaldi coined the word diffraction. So where do we get this word? We got it from this Italian scientist, Signor Grimaldi. And he was the first to record accurate observations of the phenomenon in 1660. Now, 1660 was the time of Isaac Newton. And Isaac Newton must have known of this work because Isaac Newton was one of the greatest experts on optics in his time. But somehow Newton didn't recognize Grimaldi's observations, assuming he knew about them, which is almost certain. He didn't recognize those as indicating a wave phenomenon. But really, it's the wave theory of light which explains this. Now, in this Wikipedia, it doesn't particularly emphasize light. The same thing happens for water waves. Water waves passing by a rock, or water waves passing into a harbor through an opening in the harbor walls. So there's also bending of sound waves. Diffraction occurs for sound waves. It's really a wave phenomenon. But we're focusing on the application to light waves. All right, so that's the meaning of the word diffraction. You probably haven't used that word a lot in your everyday life, but it came from Signor Grimaldi. All right, so here's in my own words. In other words, when light passes through an aperture in an opaque screen, or around an opaque object, the waves bend around the boundary. The edges cause the waves to bend. In other words, light does not travel in straight lines, as in geometrical optics, rays, when it encounters a discontinuity. Now, even in geometrical optics, light doesn't travel in straight lines because you have the phenomenon of reflection and refraction. So the light that hits the surface of discontinuity in the index of refraction will bend, either as it reflects from the surface or as it passes through the surface. That's what makes lenses possible. But you don't even need an index of refraction. You don't even need a discontinuity in the index of refraction. We're just talking about lights traveling in space. They don't travel in straight lines when they encounter an opaque edge. Or to put it another way, perfect shadows do not form in a wave theory of light. Now here's a well-known example of diffraction, which occurs in many textbooks. I don't think it's in our textbook, but anyway, you can find this picture all over the internet and all over books about optics. This is a photograph of coherent light passing through a Gillette razor blade. Now, at your age, you probably don't know what a razor blade is. You've probably never seen a razor blade. But, before there were multi-blade razors, a razor consisted of a little handle, or a little holder, which would hold a very sharp, dangerously sharp little piece of steel. That was the blade. The edge here is dangerously sharp. And it has a region cut out in the center where it gets attached to the handle. Well, okay, so behind this razor blade, there was a laser. Lasers produce coherent light. Lasers are quite remarkable in that the light they produce is coherent. Sunlight is not coherent. Light from a lamp is not coherent. Light from the sun that passes through a thin slit, the light that comes through the slit, that is coherent. Because that all comes from one particular source, one particular area. Well, anyway, this is probably laser light spread out by a lens to pass through this Gillette razor blade. And then the light that comes through is being photographed. And you see these alternating regions of bright and dark fringes. Wherever the light passes an edge, there are interference patterns. Regions where at some distance you get a bright fringe, then you get a dark fringe. Then you get a bright fringe, then you get a dark fringe. Alternating bright and dark fringes. So that's an example of diffraction. Now, we saw an example of diffraction of light passing through a razor blade or passing around a razor blade. And that's not anything very useful or practical, but there's an example in a textbook of something which is extremely useful and practical, which is diffraction gratings. So you have coherent light passes through a large number of slits in an opaque metal material. So you have an opaque metal plate, you cut narrow slits through the plate, and you have multiple openings that the light can pass through. So you have a light source, which is probably incoherent, unless it's a laser, but you have a light source. It goes through a narrow entrance slit. The light that comes through the slit is coherent. That light then is incident on this grating. It's a piece of metal with openings cut into it. This could be like a gold foil mounted on a piece of glass, and then with a razor blade you cut slits in the gold foil, making a large number of openings for this coherent light to go through. At each opening, the light spreads out and interferes with light from other regions. So that's called a diffraction grating. One way diffraction gratings are used is to make spectrometers. You have a source of light for some element, and you want to know what is the spectrum of that element. Let's say this was a source of very high temperature, I don't know, some gas, let's say oxygen, gaseous oxygen. Well, that will emit light. You want to know what are the colors of light emitted by oxygen. Well, that would probably be oxygen molecules, but if you're looking in the visible or the ultraviolet, you would say, I want to know the spectrum of light produced by oscillations in an oxygen atom, or argon, or any gas, hydrogen, helium. For each atom, there's a spectrum, which is characteristic of that atom and distinguishes it from any other kind of atom. Well, if you want to analyze the light produced by some gaseous material, you pass it through a grating and you look at the interference pattern. So these are the essential elements of a grating spectrometer. That's called a grating spectrometer. For precision measurements, an electronic detector is normally used in place of the screen. So for different angles, you have a different range of bright and dark regions, each of which depends on the wavelength. So the light is producing many different wavelengths. The light is not monochromatic, the light source. The light source, let's say it's a hydrogen high intensity hydrogen gas at high temperature, that will produce different wavelengths of light. So the light itself might look sort of white, but it's a mixture of colors, and you want to separate the colors. Well, going through the grating, different colors, different wavelengths are separated in terms of their bright fringes by angle. So there'll be a relationship between the wavelength, the geometrical properties of the grating, which will be some things like the width of the slits and the distance between different slits. So I have these different geometrical properties. I have the wavelength. If I had monochromatic light, that would be one wavelength only, or I have some set of wavelengths. So I have some set of wavelengths. And for each wavelength, there will be a set of angles where there's constructive interference for that wavelength. So you'll have a set of angles that depend on the wavelength, and the different colors of the light source, that is the spectrum of the light source, will be separated by angles. Now, I won't write down the formula for the region of constructive interference for a diffraction grating, but again, you'll find that in the book. So here's another exercise, something you should try to answer, probably by looking in the book, and write it down in your notebook because you'll need to know the formula to do the line kappa problems. What are the directions of the bright fringes produced when coherent light passes through the slits in an opaque screen? These are usually very dense. They're very close together. There's a large number of slits. You know, we considered double slit interference. Well, this might be like 1,000 slit interference. And, you know, so it'll depend on how far apart they are. Now that's an example of what's called a transmission grating. The light goes through the grating. You know, the grating is a piece of metal. Normally light doesn't go through a metal, but it's got these thin slits cut out with a razor blade. So now the light can go through the metal, and you get on this side a diffraction pattern. That's called a transmission grating because the light goes through the grating. There's another kind of diffraction grating called a reflection grating, where you have the light not going through the metal, but reflecting from the surface of the metal. And you don't have complete apertures cut into the grating, making up the grating. You just have little grooves cut into the surface. So in a reflection grating, you have grooves cut in a metal surface and light reflected from those grooves. And so each groove acts as a little source. Just like in a transmission grating, each slit acts like a little source. And there's the same kind of diffraction pattern produced in reflected light. This is explained in the book, and an example that's given is a CD, the surface of a CD, or the surface of a DVD. You've certainly looked at the surface of an audio CD, a compact disc, and white light reflecting from the surface of an audio compact disc or a DVD shows the colors of the rainbow. Because for different angles, there'll be different wavelengths that are undergoing constructive interference. And so at those angles, you'll have predominantly the intensity of that wavelength, that corresponding wavelength. And so it'll reflect. It won't reflect like a mirror. It won't produce white light reflection. It'll separate the light into different colors. So although the surface of a CD is highly reflective, you can't look at your image in a CD. But you know what you see if you look at light reflecting from the surface of a CD, you see the colors of the rainbow. So there's an example of that in the textbook where you have to calculate, you know, what's the angle for, let's say, constructive interference of red light in a compact disc. It's probably also a line kappa problem. So, you know, read the example in the book, and then once you've grasped it, then try to do the line kappa problem. Now there's one more section in chapter 22, which is actually a little bit different. It's section 4. It's called polarization and scattering. It's not so much, well, it's wave optics. It is wave optics, but it's not so much concerned with interference. There's a section on polarization, the fact that the electric field can be oscillating. Let's say the light is traveling in the z direction. The electric field could be oscillating in the x direction, or it could be oscillating in the y direction, or it could be oscillating in any direction perpendicular to the z direction. If it's unpolarized light, such as light from the sun, it would have oscillations in all the directions perpendicular to the z direction. That's unpolarized light. But there are materials that have been developed which polarize the light. So when light, which is unpolarized, passes through what's called a polarizer, it comes out on the other side with only one direction of oscillation for the electric field. That's one polarization. So that's the phenomenon of polarization. It's separating the wave by the direction of oscillation of the electric field. Now, there are polarizers which do that. It can also happen as a result of reflection. So, in fact, the first observation of polarization was polarization by reflection. It can also be produced in certain crystals. So, calcite, some calcium crystal, reflected unpolarized light will separate into two different polarizations. The other part of it has to do with scattering, which is another optical phenomenon. Light hitting an object and scattering off it. So suppose we had light coming in like this. Coming in like this and hitting a little drop of water. Well, the light will come out in all directions, and that's called scattering. Light hits an object, in this case, not a piece of metal, but a dielectric material, water. There'll be reflection and refraction at the surface of the water droplet, and there'll be outgoing light, which will be, the intensity will depend on the angle, so there's a scattering intensity, and the colors may be separated by dispersion. That produces a rainbow. So here's a picture of, taken from the book, of polarizer. So you have unpolarized light, the electric field oscillating in all directions. But when it comes through the polarizer, because of the material property of the polarizer material, the light that comes through only oscillates in one direction. So the intensity of light after it goes through the polarizer is about 50% lower than the intensity of the incident light, because half of the light, the parts which are oscillating perpendicular to the polarizer direction, those are cut out, those are absorbed. The rest of the light comes through, so it has about half the intensity. So it says here, parallel polymer fibers in polarizer transmit only component of E perpendicular to the fibers. And so downstream of the polarizer, you have polarized light. A polarized light has some interesting properties compared to unpolarized light. If you put a second polarizer here, you can cancel the light if the second polarizer is perpendicular to the direction of the first polarizer, because the first polarizer cuts out all of the oscillations in one direction, leaving only the perpendicular direction. The second polarizer cuts out all the light with that direction of oscillation. In other words, nothing comes out of the second polarizer. So two crossed polarizers with cross directions. This one has got this direction. This one's got the 90-degree different direction. Cross polarizers are opaque. But on the other hand, if this polarizer is not crossed but is in the same direction as the first polarizer, there will be no reduction in the intensity of light coming through the second polarizer. So you get variation of intensity that depends on the relative angle of the two polarizers. So you have intensity depending on the angle between the two polarizers. You know, if it's 90 degrees, you'll get 0 intensity. If it's 0 degrees, you'll get 100% intensity. And for an angle between 0 and 90, there's a formula which is called Malice's law. And I won't write it down in the screencast here, but it's in the book, and you'll need it for some of the law and kappa problems. So that's the case of polarization. What about the case of scattering? Well, there's a very interesting phenomenon involving scattering. Scattering of sunlight from molecules in the atmosphere. You know, the atmosphere is made up of nitrogen, oxygen, molecules, argon atoms. Argon doesn't form molecules. A little bit of water molecules. I'm not talking about little drops of water as I was here. I'm talking about water molecules, water vapor, the gaseous form of water, H2O molecules. Well, when light scatters from a small object like a molecule or an atom, that is described by the theory of Lord Rayleigh. It's called Rayleigh scattering. And Rayleigh scattering says that the intensity depends on the frequency or wavelength of the scattering light. The intensity is proportional to the fourth power of the frequency. So for scattering of light from molecules, the intensity of the scattered light, the incident light is sunlight, is white. The intensity of the scattered light is proportional to the frequency to the power 4. High frequencies have a higher intensity, low frequencies have a lower intensity. So this explains why the sky is blue. Sunlight is a mixture of all the colors, but the blue wavelengths are scattered more than the red wavelengths or frequencies. And so the sky is blue. The skylight is scattered sunlight. Scattered by what? Scattered by molecules. That's described by Rayleigh's theory. That was worked out in the late part of the 19th century. So before the 19th century, before the late part of the 19th century, mankind had no explanation why the sky is blue. After Lord Rayleigh and his theoretical analysis, now we know why the sky is blue. As opposed to clouds. Clouds are white. I'm not talking about when you have dense clouds like on a rainy day. I'm talking about when you have those big puffy clouds where sunlight scatters from the clouds. Sunlight is white. Clouds are not made of molecules. Clouds are made of, well, everything is atomic, but clouds are made of drops of water, not molecular-sized scattering centers, but much larger, little drops of water, maybe a millimeter in diameter. And those little objects scatter the light equally for all wavelengths. So the light scattered by a cloud will have the same color as sunlight. It'll be white. Why are sunsets red? Well, I'll leave that as an exercise for you. That's explained in one of the figures in chapter 22, but it's related to the fact that the sky is blue. Sunsets are red. And I'll let you read about that. Well, okay, so this is kind of an introduction to chapter 22. I haven't given any equations, so this is just the introduction. Now you need to go and find out what are the equations in order to do the ln kappa exercises.